Get out a calculator, not your phone. Get the calculator out that you're going to use on a test. All right. You don't need to like write this procedure down. You just need to write two numbers. I want to know how much you weigh in newtons and how much your mass is in kilograms. Okay. You don't need to memorize this procedure. I'll tell you this. I just needed these numbers. Okay, so to find your weight in newtons, take your pounds and multiply it by 4.45. And write that just off the side, that number. That's your weight in newtons. Take your pounds, multiply it by 4.45. Okay. Write that off to the corner. That's your weight in newtons. Okay. Then you also need your mass in kilograms. So take your pounds. Again, start with pounds. How much you weigh, pounds, and divide by 2.2. That is your mass in kilograms. Write that somewhere. Find your weight in newtons, multiply your pounds by 4.45. To find your mass in kilograms, divide your pounds by 2.2. Okay? So that's all we're doing. I just want to make an example that is very personalized. So, nope. You just need to write them down for the next slide. That is the extent of what you need to know this for. Good with that? Thumbs up when you're good. So what we're going to do is we're going to calculate the gravitational force between you and the Earth. Okay? So gravitational force is G m1 m2 over r squared. Okay, so your gravitational force is going to be 6.67 times 10 to the negative 11th. Now, before we go on from here, I need you all to know how to type in your calculator's scientific notation. Okay? Do not, this is very junior high-ish, 6.67 times 10, look for the caret, negative 11th. There are shortcut buttons. Okay? If you have a Texas Instrument, one of these, you're looking for the EE button right there. Okay? The EE button on this design is a second function above x to the negative 1. That takes care of times 10 to the. If you have a Casio, you are looking for the EXP button right there, or the times 10 to the X button. If you have a Casio, EXP or times 10 to the X button. Okay. So what you will type is 6.67 EE or EXP negative 11, not subtract 11, but the negative sign. Okay. If you have one of these calculators, yes, times 10 to the n, and you need to use parentheses like crazy for scientific notation. They just don't deal with scientific notation well. Okay? All right, so the mass of you, this is yours in kilograms, times the mass of the Earth, 5.97. times 10 to the how many zeros? 24. Boom. That's a chunk. Divided by, okay, so the two objects are you and the Earth. Great question. It does not, the question was, how do you know which one's M1 and M2? Doesn't matter. One of them's one of them's one object, one of them's the other one. Okay. R is the distance of separation between the centers of the object. Here's the center of Earth. Here's the center of you. R is that distance there. So how would you go about finding that distance? Like what measurements would we use? Not necessarily to measure that, but just to like, oh, you'd use this and this. Brandon. Okay. That's how you could find it. What we're going for is the radius of the Earth plus half your height. But when we're talking about the radius of the Earth plus half of your height, adding your half your height to the radius of the Earth, that's like adding a bucket of water to the ocean and going, "Up, I just raised the sea level." Yes, sir. No, you didn't. So all you need is the radius of the Earth. Okay, so we find the radius of the Earth to be 6.38 times 10 to the 6th meters. Make sure you square that. Okay, do that calculation. You need to make sure that everybody knows how to use their calculator. And to test to see if you got it right or not, you're going to take that number that you calculate and divide it by your mass in kilograms, and you should see a number that you recognize. Mm-hmm. Please call me over if you have questions or like how does this work or anything like that.
Every time I do that.
Oh, do this. Second. That takes care of times 10 to the negative 11.
Okay.
Okay. Yep.
It just gave me. It didn't give me a number. Same thing.
Right. So multiply all those out.
I'll
Be right with you.
I got after doing it. What do I do with this number now?
Divide by the mass of you. Divide by your mass.
Wait, how'd you see the negative 11?
So you go 6.67 E. That's times 10 to the negative 11 times your mass. We'll just say 61 times 9.96. Meh. Okay, you keep going. So then, you gotta do the times 10 to the. So, okay, we're gonna. You start do that. E is times 10 to the negative 11 times your mass times that. VE times 10 to the, there you go, divided by. Okay. All right. Yeah. Yep. Make sure you square the radius. That's a very popular error. Not dividing by or not squaring the radius. Questions, points of confusion. Lots of parentheses. Here's that one doesn't like scientific notation. No. Yeah, I don't know what you did. Try it again. Yeah. Then divide that by your mass to see, see something. Beautiful. All right. When you divide by your mass, what did you discover? Roughly 9.8. Crazy. What? Okay. Here's the deal. The force of gravity equals gravitational force only on or near surface of the Earth. Okay, the gravitational force equals the force of gravity on or near the surface of the Earth. Okay. You know how a square is a rectangle, but a rectangle isn't a square? That makes sense. Like a square is a special case of a rectangle. This is the square. This is the rectangle. This is the force of gravity only on or near the surface of the Earth. This is the force of gravity anywhere in our known universe. You okay with that? So, up until this point, we didn't care about anything other than on or near the surface of the Earth. That was all about last semester. And that was equal to mass times 9.8. Force, gravitational force is that. Okay. Now, if we take this and we divide by your mass, which is what we just did, that gets us, that's why you got 9.8. You okay with that? Okay. Here's the crazy thing. You can use this equation to find out how much you would weigh on any planet, on any moon. You can use what we just did to find the acceleration of gravity on any planet or any moon. Right there. Cool with that? Okay. Questions there? Okay, so when okay, so let's fast forward, let's say 5, 6, 7 years, and you have graduated from college. You're now in the workforce. Your boss comes to you and says, hey, I want you to solve a problem. And you go to your computer and you do some preliminary research to figure out what stuff. He's like, Google, ChatGPT, tell me about. And the computer spits out a ton of information. It's a very worthwhile skill to be able to discern, hey, this information is important, this rest of the stuff isn't important for the problem I'm trying to solve. Does that make sense? Like that is a very employable skill. Okay. I'm not suggesting that you're going to be like trying to figure out physics problems, but I'm going to give you more information than you need to know. You're going to need to be able to sort through what information is relevant to what you're trying to solve for and what is just extraneous. Okay, does that make sense? Okay, so I don't want you to calculate this. I just want you to pick with this information how would you go about figuring out how much you weighed? What was your weight on Mars? Go ahead and tell your neighbor what information you would use. Correct answer is the diameter. You're going to divide that by 2, find the radius, and you're going to use the planet's mass and your mass, and you're going to be good to go. Good with that? Okay. How did you find the acceleration of gravity on Mars? One way to do it would be employing just this equation here. Another way you could do it is recognize, hey, on Earth, you have this relationship. So once you have this, you can use the same trick. I don't like using G because G is like set apart for just 9.8. So the way that I kind of denote that is this is acceleration of gravity on any planet or moon. That's the same pattern, same equation, I guess. Cool with that? Okay. Give that one a shot. Thumbs up when you have a guess. Have a conversation. Correct answer is? Correct answer is A, 1/4 of your weight. When you're here, you're 1 R away. Going 1 R above the surface, we've doubled that distance. So when we double this distance, that needs to be squared. Good with that? Okay. So what this demonstrates is how, like, your weight drops off really fast. The force of gravity drops off really quick as you go away. That's a consequence of the inverse square law. It decreases really quick. Okay. All right. So you hit this in the pre-quiz. In an orbit, the thing playing centripetal force is gravitational force. Okay. That right there is, if you have an orbit, this is what you're starting with. What's playing the role of centripetal force? Gravity. Okay. Now, we know that centripetal force is equal to mass times speed squared over the radius. We also know that gravitational force is equal to G m1 m2 over r squared. So what we're going to do is we're going to take that expression, that equation, and substitute it in here. We're going to take this equation and substitute that in there. So what we have is mv squared over r is equal to g m1 m2 over r squared. Okay. Good with that? So first off, notice there's a lot of m's up there. Could we simplify any of those? Okay, so M1, M2 doesn't really matter which is which. Mass of Earth, mass of Sun. Okay, but what mass is that? Is that the mass of the Earth, mass of the Sun, the combination of mass and Sun? Like, so a leading question is, which mass is experiencing centripetal force? The Earth or the mass? Sorry, the Earth or the Sun?
The Earth.
Earth. So this is the mass of the Earth, and that can simplify. Here it's canceled out. That makes sense? Okay. All right, we've got some R's on both sides. Is the R in this equation the same as the R? I know it's the same letter, but does it represent the same measurement? The R in this is the radius of the circular path. So that would be that dimension there. The R of this is the distance between the center of the Sun and the center of the Earth. Is that the same thing as this? You okay with that? So one of these can be simplified. So what that leads us with is speed squared is equal to g, the mass of the sun, over r. And if we take the square root of both sides, what this yields, what we're left with, is this is the speed required to maintain a circular orbit. The speed required to maintain a circular orbit. And this m is the mass of the center object. Mass of the center object. Okay? So what we find is the speed that of anything that's going in a circular orbit is dependent upon this gravitational constant, the mass of the center thing, and the distance away from the center thing. Okay? It is not dependent upon the Earth's mass. So what that means is if I can take a tennis ball and I can throw it the same speed the Earth is going, the same distance away from the sun that the Earth is, I can put that tennis ball in orbit, share the orbit with the Earth. It doesn't matter. The mass of the object in orbit, it's independent. Got canceled out. Okay. Consequence to that, if you're familiar with your solar system, you've got Mercury, Venus, Earth, Mars, Jupiter, but between Mars and Jupiter, what do you have? The asteroid belt. Okay with that? Are the masses of the asteroids all the same? No, it's a conglomerate of a bunch of stuff, but it doesn't matter because they have a certain speed, a certain distance away from the sun. They're maintaining an orbit. Cool with that? Or think about Saturn's rings. Cool with that? Okay. Now, this equation I'm not going to give you. I will give you this equation. I'll give you this equation. But I'm putting on you to build this equation. You can memorize it, sure. Okay. But I need you to understand this process. In math terms, this is called deriving the equation. Okay. You need to be able to do this. Like, oh, it's an orbit. Oh, centripetal force is equal to gravitational force, and cancel those out. Okay. I will write test questions that determine did you just memorize this or do you know where it comes from? Okay. Okay. So I want to verify that the Earth's period of revolution is 1 year. around the sun. Okay? So what we're going to do is we're going to employ that. Okay? So I want you to figure out, using this equation, the speed that the Earth needs to go. Okay, I've given you information here. I'm going to give you a minute head start. You should calculate the speed of the Earth as it goes around the sun. What mass did you use? The sun's mass. What R did you use? This R here. 1.5 times 10 to the 11th meters. And then he takes the square root of all of that. And your answer should be 29,747 meters per second. Remember to take the square root. Thumbs up if that's what you got. It would really stink to go through tonight's homework and not know how to use your calculator. Make sure you can get this number. Okay. So once we have that, we're asked to find the period. The only equation that has a period in it is this one. Speed is equal to the circumference over the period. So I've got 29,747 is equal to 2 pi r. What r should we use? Think before you answer. Earth's radius, bless you, distance from Earth to Sun, or Sun's radius. This is the distance going around here, so r is going to be, again, 1.5 times 10 to the 11th meters. Okay. Hey, here's another trick. Did you know you had a button on your calculator that recalls the previous answer? It is a really nice feature. The button says ANS. that recalls, that brings up the answer that you just had. That prevents you from having to write that down every time. So I've got 2 times 5 times. Oops. Okay. Real quick here. Do not try to get t by itself by going, oh, okay, 29,747 divided by this. On that side, that would leave 1 over t, not t. Everybody, does that make sense? Okay, popular mistake. Here's my recommendation. You got an unknown in the denominator. Get that out. That is priority number 1. Okay, I was just bringing that over here. So 29,747 t is equal to 9.42 times 10 to the 11th. So t is equal to 9,047. It's equal to 31,683,121. And what's the unit on that? Seconds. How many days is that? Well, there are 60 seconds in a minute, so divided by 60. 60 minutes in an hour, divide that by 60. 24 hours in a day, divide that by 24. And we get this crazy number that says 366.7 days. Is the Earth's orbit a perfect circle? Nope, but it's really stinking close. 366.7 is really close to 365.25 days. Wow, physics, crazy. Go to that. All right, so popular question is, well, what happens if we don't have this speed? Okay, if we don't have this speed, if we're going slower, then what happens is it'll still orbit, it'll just look elliptical, where the sun is one of the foci. But what would happen to our climate, life on Earth, if that was our orbit? I think global warming is a thing now. Okay, and if it's too slow, okay, if our ashes could somehow like stay together, it would still do an elliptical path, but you get incinerated. Okay, if it's faster than this specific speed, it's still in orbit. The sun's at one of the foci, but what would happen to our climate? Freeze. Like, okay, good with that. So it's really nice that our Earth is really close to the circle. Like Halley's Comet has an elliptical path that's like crazy flat, coming back every 90 years or so. Okay. If we're too fast, follows a hyperbolic path and is not coming back. Good with that? Tell your neighbor. Correct answer is E. Nothing will happen because the mass of the Earth got canceled out, independent of the Earth's mass. Doesn't matter. Okay. Next question. My recommendation, because you got three variables that change, make one fixed and see what happens to the third variable. Does that make sense? And then flip-flop the one that you fixed. Have a conversation. Okay, correct answer is D, domesticated dingoes. Okay, here's the idea. So let's say, so we're going to decrease the mass of the sun. Let's say we keep this the same in order to, oh, that squared is not there. In order to maintain the left side to be the same, the R has to go down. That's one. Okay. Let's say we keep the R the same, the distance the same. So the mass goes down of the sun. That's going to make your speed has to go down. See how I did that? Does that make sense? Keep one the same, and then you see what happens to the other one. Okay. for the sake of time, last question. Correct answer is B, gets longer. Here's how you do it. So as your radius goes up, your speed goes down. Okay, I'm going to rearrange this for period. Oops, that's a V. As your radius goes up, your period goes up. As your speed goes down, your period also goes up. So both of those factors make the period go up. So Neptune takes a lot longer to go around. So you wouldn't have very many birthdays if you lived on Neptune. Got a worksheet due tomorrow. Yes.